Hello, let's continue with our discussion of classification of constraints. So as I told you in the previous video that the constraints present in a system is classified into several categories based on different criteria. One of the classification we have already started discussing, which is known as holonomic and non-holonomic constraints. So we have seen that those constraints which can be expressed as an equality is what is known as holonomic constraints. Holonomic constraints are otherwise known as integrable constraints. Integrable constraints. So that is yet another term that is used for holonomic constraints. Integrable constraints. Okay. Well, constraints. Because an equation can be suitably rearranged and we can integrate it over. Now see, we have discussed I think one example of a holonomic constraint. The constraint that exists between the two masses in a dumbbell. Okay, because we have seen that the distance between the two masses L is equal to a constant, and so you can write that in terms of the coordinates of the two masses x2 x1 y2 y1 and z2 z1 as an equation. So this thing is an example of a holonomic constraint. You can have several other examples of holonomic constraints. For example, just you consider the motion of a pendulum. Okay, motion of a pendulum. See a simple pendulum. So say let this be the pendulum. Okay, consider this is a string and there is a mass or the bob. Let the length of the string be L, right? Okay, so this is a system containing only one object. So the number of particles is equal to 1. So I can say here number of particle n is equal to 1. And the motion of a pendulum, motion of a ordinary simple pendulum, that will be restricted to a plane, right? The motion is restricted to a plane. So in order to explain the motion of this pendulum, if it is oscillating in xy plane, say suppose that it is oscillating in xy plane, then to specify the position of the mass or configuration of the bob, you need to have only two coordinates, right? X and y. That is enough. If you are using Cartesian coordinates, only two coordinates is enough. Any position of the bob can be explained by using two of these coordinates. Okay, or if you are preferring to use the plane polar coordinates, then you can call this one as this angle as theta. Suppose this is the orientation. This is the orientation. So there will be an angle theta. Theta is the angle made by the string with the vertical. Okay, so when it is swinging, the value of theta will be just varying between 0 and some plus or minus theta max. So just if you specify the length of the string and the theta, right? Okay, you will be able to just explain. So I can say instead of x and y, you can just specify r theta or L theta. Then also you can explain. But one thing you have to be clear about, so the degree of freedom, as per our calculation, degree of freedom might look it's equal to 2 because it's motion in a plane. So two-dimensional motion. So we may feel that the degree of freedom equal to 2. But when you analyze, you can see that the length of the pendulum is fixed, right? So the length of the pendulum is actually what? Fixed. It's a constant. So L equal to a constant. So how do you write this L? The length of the pendulum can be written as what? X square plus 0, right? So if this is origin, you say if this is origin 0 0, then I can write this one as what you can represent this one as what L equal to a constant, or you can just write simply x square plus y square, is it not? X square plus y square is equal to, right, or x square plus y square plus z square, whatever it is, x square plus y square, that is equal to this L square, right? So we can just use in that way also. Now if this is L, right, you can just take it even it is oscillating. Now so this is an equation. So this equation is once again representing a constraint which is expressed as a an equation. So we will call that this type of a constraint, that the length of the string is fixed, constant is yet another example of holonomic constraints, right? So we can say actually there is you need not take 2 degrees of freedom. Instead, you can reduce the number of degree of freedom by 1 due to the presence of a holonomic constraint. So the actual degree of freedom for this system, simple pendulum, will be reduced from 2 to 1. So 2 minus 1, it is equal to 1, where 1 is the number of holonomic constraint that is present. So it is enough to mention theta. So theta is the single coordinate that is enough, right? So that is independent coordinate. Okay, the other thing is related. So either specifying x or specifying y is enough, because when you specify x, automatically y can be defined from that equation. So sorry, I should write L square. Okay, that is the other thing can be just obtained. That is why we say the number of independent coordinates, the minimum number of independent coordinates required to specify the orientation or the configuration of a system is known as the degree of freedom. Now, several other examples you can take. For example, you consider the motion of an insect moving over the surface of a sphere. You have got a sphere and you consider an ant is moving, or some insect is moving over the surface. Now see, since sphere is a three-dimensional object, sphere is a three-dimensional object, you know, in order to specify its motion, actually we may need to have x, y and z, right? X, y and z may be needed. So if particle is somewhere here, I can use either x, y, z, or I can use the spherical polar coordinates like r, theta and phi. So any of this combination will do. Okay, so we may feel that see, the degree of freedom is equal to 3. We may feel that degree of freedom equal to 3 because 3 coordinates are required. But you will see that here there exists a constraint for the motion of the insect. What is the constraint? The constraint is that the ant cannot move into a region within the sphere, right? It's a hard sphere, so the ant can move only over the surface of the sphere, so it cannot move into a region within the sphere. Okay, or I can say the ant can move, also the ant cannot move outside. So we can say that the constraint here for the motion is that always the x, y and z of the ant, x, y, z coordinates of the ant or the insect will be limited to the condition x square plus y square plus z square is equal to, say, r square, where r is the radius of the sphere. If r is the radius of the sphere, then this will be, okay, x square plus y square plus z square is equal to r square will be the relationship that exists between x, y, z coordinates of the ant or the insect. So there exists one constraint, okay, and that constraint is expressed as an equation or as an equality. Hence, this is also what the constraint present here is also regarded as what? A holonomic constraint. Okay. Now similarly, you can just consider like you have considered what is known as single pendulum or simple pendulum. You can consider what is known as double pendulum. So what is meant by a double pendulum? You will have a rigid say just rod may be connected to a mass em, and at the end of the mass em there will be another pendulum connected. Okay, so these two, so say that this is L1 and this is what, L2. Okay, so these two masses are there. So these two pendulums are coupled pendulums. Okay, so one pendulum connected to the bob of another pendulum, and they can just oscillate independently of each other, right? And see, in this particular case also we can just say that there are two masses. If there are two masses and if they are swinging in a plane, we expect that in order to explain the configuration of the first mass, we need to have x1, y1, and in order to specify the second one, we need to have x2, y2 if we are using Cartesian coordinate system. Or I can say I needed r1 theta 1 here, and here we needed what, r2 theta 2. You may feel it like that, but you know that there exist two constraints here. The constraint is that L1 equal to a constant, and the second constraint is that L2 is equal to some other constant. So there are two constraints represented by equations. So we can say there are two holonomic constraints. So the actual number of degree of freedom would have been for a two particle system, it should have been 2 into is not okay in a plane, so it will be 2 into 2, it should have been 4, but due to the presence of two holonomic constraints, which can be represented by two equations here. The actual degree of freedom will be reduced by 2. So degree of freedom will be equal to 4 minus 2, which is equal to what? 2 only. And what are that? That they are actually theta 1 and theta 2. So theta 1 and theta 2 are the two quantities that is required to specify the configuration. So where you can say theta 1 is the angle made by the first rod, and theta 2 is the angle made by the second rod with the pendulum. Okay. So similarly, you remember that in the case of a rigid body, so rigid body is a body consisting of n number of particles, such that the distance between any two particles is always a constant. Is not rigid body. A body composed of an n particle system, such that the distance between any two particles on the body is a constant. So that is the way in which we define a rigid body, and we have got an entire module to explain the rigid body motion. So we will discuss detail about rigid body motion in that module later. But always remember, that suppose that this is a rigid body, this is some rigid object, okay, having a definite shape and size, and you consider any 2 points here or any 2 particles of the rigid body. It's an n particle system. So this is the ith particle and this is the jth particle. The condition to call this object as a rigid body is that the distance between I and j, or ith particle and jth particle, should always remain constant. So I can say, if I call the distance between these two particles as some rij, the condition for this object to be a rigid body is that the distance rij should be equal to some constant, say c1. So you can see that this is some sort of constraint that exists in the case of a rigid body. And even though a rigid body is composed of n particles, later we will be able to prove that, argue that even though it is an n particle system, okay, free to move in space, the degree of freedom of a rigid body is limited to 6 only. So this is something very, very important. See that this as a special case, you try to understand this one. We will explain this one logically, and we will argue it later in the later module, because we cannot spend time on that one right now. So the degree of freedom of a rigid body free to move in space will be 6 only. And why this 6, you will understand. Out of this 6, 3 will be corresponding to the translational degree of freedom, and the 3 will be corresponding to what is known as rotational degree of freedom. Okay, means 3 will be required to specify the center of mass of the system, and the other 3 degree of freedom will be used to describe the orientation of the body. So 3 for rotational degree of freedom and 3 for translation degree of freedom. Altogether only 6 degrees of freedom. Even though the rigid body is made up of n number of particles, we expect that there should be 3 into n number of degree of freedom, but it's not the case. There will be only 6. It is other degrees of freedom are said to be redundant. Okay, they are frozen degrees of freedom, I can call in another way. So that is about holonomic constraints. So similarly, we can discuss non-holonomic constraints also. Before going to the discussion of non-holonomic constraints, I think I can just discuss non-holonomic. What are non-holonomic constraints? Non-holonomic constraints are, or non-integrable constraints. So non-integrable, non-holonomic, or another term used is non-integrable constraints. Other one is integrable constraint. Non-integrable constraints are those constraints which can be expressed as an inequality, which cannot be expressed as an equality, but it can be expressed as an inequality. So I can give you some example. You consider a bird or an insect flying over the surface of a sphere. Say a bird flying over the surface of Earth. Okay. In the case of a bird flying over the surface of the Earth, since the bird is flying in space, it's a single object, right, having mass m. Since it is moving in space, its degree of freedom should be x, y, z. When you have to specify the motion of the bird, you can use a Cartesian coordinate system with the x, y, z as the coordinates. So you can see the degree of freedom here, small n is equal to, small n represents the degree of freedom. Here small n is equal to 3. Okay, but even though in the degree of freedom equal to 3, it has got a constraint. What is the constraint? The insect or the bird cannot enter into the earth. Into the earth means inside the earth. So if earth is having a radius r, I can say there exists a constraint which can be represented by the equation something like x square plus y square plus z square, where x, y, z are the coordinates of the bird. That should be always greater than or at the most equal to what? R square. That should be greater than or at the most equal to what? R square. Right? Means there the bird cannot be inside less than that R value. The x, y, z combination should not be less than the R value. Right? So that is and you can see that here the constraint is not represented by an equality, but instead it is represented by an inequality. Okay, so these type of constraints are what are known as what? Non-holonomic constraints. Non-holonomic constraints. There can be some other examples also, like so you consider some gas molecules in a container. Gas molecules in a container. You consider a spherical container. That is easy to deal with because you need not talk about the sides and all. Then you need to mention only the radius. So suppose there is a spherical container with some radius, you say small, r, or the radius vector is r vector. Okay, so let r be the radius of the spherical container, and there are large number of what gas molecules inside it. Okay, so you can see that there exists a constraint. What is the constraint? The constraint is that the molecule can move well inside the sphere along x, y, and z direction, but there is a condition that the position vector, or I can say the magnitude of the position vector here should be less than or equal to, you say, a. Let me say a is the radius of the sphere and r is the position vector of the particle. Okay, from origin you take an arbitrary origin at the center of the sphere, and let me say that r is the position vector. So the magnitude of the position vector will be always less than or equal to a. Means the molecules are constrained to or limited to move within the sphere only. Right? So you can see that once again here there is an inequality that is coming, not an equality. So those constraints which can be represented by inequalities are what is known as what? Non-holonomic or non-integrable constraints here. And the speciality, I think you would have noted by the time, that we have seen the presence of holonomic constraints reduces the degree of freedom of the system. The presence of holonomic constraints reduces the degree of freedom of the system. If there are two holonomic constraints, then the degree of freedom of that system will be reduced by 2. If there exists one holonomic constraint represented by one equation of constraint, then we will say the number of degree of freedom of that system will be reduced by only 1. Or I can say the presence of holonomic degree of freedom will reduce the presence of holonomic constraint in a system will reduce the degree of freedom of the system. But the presence of non-holonomic constraints, as we have discussed in the examples of the gas molecules or the bird flying over the earth, it will not affect the already present degree of freedom. Non-holonomic constraints will not affect the number of degree of freedom of a system. You can understand. Okay, why? For example, the bird is flying over the earth. So since the bird is flying in free space, it has got 3 degrees of freedom, x, y, z. Okay, even though it cannot enter into the bulk of earth, earthinte ullilekku adinu kadakkan pettunnilla engilum birdinu 3 degree of freedom undu. It can move in space, right? Okay, so you can see that even though it has got a constraint, its degree of freedom is still 3. Right. So you can see that the presence of the constraint is not affecting the number of degree of freedom if the constraint is a non-holonomic one. So you can have a conclusion. The presence of holonomic constraint reduces the degree of freedom of the system, or degree of freedom can be calculated as degree of freedom is equal to degree of freedom. You first calculate degree of freedom without constraint by simple logic. Degree of freedom without constraint for n particle in space, 3n degrees of freedom. That is our general idea. Then you subtract the number of holonomic constraints from that. or I can say the degree of freedom of a system, degree of freedom represented by small letter n, it is equal to, for an n particle system, okay, for an n particle system with k holonomic constraints, the degree of freedom of the system will be equal to 3n, that is the degree of freedom without considering the constraint, minus k. So this can be taken as an general expression for the degree of freedom in the case of a holonomic constraint, right? So where n is the number of particles of the system and k is the number of constraints or number of equations connecting, okay, the coordinates, number of constraint equations. K is the number of holonomic constraints. That is something very, very important. Holonomic constraints. So that is about the classification of constraints into holonomic and non-holonomic. Try to find out more examples that will help. Okay. Now the second classification is into rheonomous and scleronomous constraints. So what is the meaning of rheonomous and scleronomous constraints? It is based on the time dependence of the constraint. So if the constraints are, or if the constraints involves time explicitly, if the constraints involves time explicitly, then they are known as rheonomous constraints. Rheonomous constraints. So those constraints which involves time explicitly. So depends, constraints which involves or depends time explicitly. Explicitly means directly. Example, you consider the motion of a pendulum with an extensible string. Usually the standard simple pendulum, the pendulum string should be inextensible. That is one reason why we are using cotton threads in our experiments. So if the string is made up of some extensible type of string, for example, if instead of thread I am using rubber band, instead of thread I am using rubber band, so what will happen? You cannot take that L equal to a constant. Instead, L will be a function of time. The length will be a function of time. It will depend upon the tension on the string, and the tension on the simple pendulum varies from position to position. So you can say that in that case the equation of the constraint can be written as what? X square plus y square, where x and y are the coordinates of the pendulum bob. That will be equal to L of t whole square. So I cannot say that it's a constant always, but it is a time dependent constraint. So time dependent constraints are what are known as rheonomous constraints. So what are these scleronomous constraints? Those constraints which are independent of time. For example, you can take the counter example of this one. What is that? If the pendulum bob is if the pendulum bob is having an inextensible string, okay, നീളം കൂടാത്ത ഒരു ചരടാണ് ഉപയോഗിക്കുന്നത് കരുതുക ordinary കേസുകളിൽ. If the pendulum bob is consisting of it is connected by an inextensible string, then you can see the constraints will not depend upon time. So I can say those constraints which are independent of time, or there is no any explicit dependence on time, independent of time, are what are known as what? Scleronomous constraints. So the example is that x square plus y square is equal to, in that case I need not write L of t square, I can write simply as what? L square. Okay, so that is based on the time dependence. Now there are so many other classifications as well. Another classification is constraints can be considered as what? Conservative and what? Dissipative. So what is the meaning conservative and dissipative? If the total mechanical energy of the system is conserved during the constraint motion, then the force of constraints do not do any work. So we'll say that it is what? Conservative system. So based on if okay, I can say that the force of constraints, if the work done, that is better, okay, if the work done by forces of constraints, is equal to 0, then we'll say those things are conservative constraints. Now if the constraint forces do work, there are cases where the constraint forces will do work, then the total mechanical energy of that system will not be conserved, or it will be dissipated. Okay, so those types of constraints are known as dissipative constraints. So dissipative in the sense that the constraints which will cause dissipation of the mechanical energy of the system. Usually it is understood that the time dependent constraints are generally dissipative in nature. Okay, so that is a broad classification of what constraints into various categories. So always remember, constraints are restrictions or limitations on the motion of particles of the system, and the presence of holonomic constraints will be such that it will always reduce the number of degree of freedom of the system. Okay, and if there are k number of holonomic constraints present in a system, which is represented by k equations of constraints, then the number of degree of freedom of the n particle system is given by 3n minus k, where k is the number of holonomic constraints. You can just evaluate it with several example. For example, you take the dumbbell itself. You know, dumbbell is a two particle system. So what will be the degree of freedom? In the case of a dumbbell, n equal to 2. So 3 into 2 here, 6 minus how many equation of constraint? In the case of dumbbell, there is only one equation of constraint given by this equation, L equal to constant. So there is only one equation of constraint. So 3 into 2, 6. 6 minus 1, that is equal to what? 5. We are able to get the answer as what? 5. And the answer, we obtained 5 here also. You can see that with the direct logic. So you have to always reduce the number of holonomic constraints, and non-holonomic constraints will no way affect the already present degree of freedom. Okay, so that is about the thing. So try to practice more problems with calculation of the constraints and identifying the nature of the constraints. We will be discussing more about the effect of these constraints when we go to the Lagrange's equation of motion and related concepts. Okay, thank you.